All right, so welcome everyone to our second session of today and last session of this theme, which is computation and policymaking welfare. We are pleased to have Samsun, Kyogo, and Meira in this session. We start by Samsun presenting his research. So I just briefly introduce Samsun, and then I will leave the stage to him to tell us about his research. Samson Knight is a graduate student in economics at Brown, working on research at the intersection of machine learning and economics. He also holds an MFA in fiction from the Iowa Writers Workshop. Today he's going to tell us about his work on machine learning and policymaker values.
Great. Thank you so much for that introduction. Yeah, so today I'm going to be presenting to you some joint work with my advisor, Daniel Björkegren, who I think you guys heard from earlier in this symposium, as well as Josh Blumenstock at Berkeley. And this work is entitled Machine Learning What Policymakers Value. And sort of the broad framework of questions that we're trying to address here is that policymakers are pretty much always making allocation decisions between really hard to compare objectives. So the flagship example is usually that governments are trying to give welfare to those who need it most, for the people for which like aid would be the most effective. But also they want to give welfare to sort of, they might want to give welfare to the poor just because we value helping the poor more than helping wealthy people, because we view them as sort of more intrinsically deserving of government aid. And the tricky part of then evaluating government allocations is that depending on what framework we're using for what goal the government is trying to achieve, it could lead you to a different type of optimal policy design. So it creates this kind of apples and oranges framework where it's hard to actually decide whether a design that better prioritizes the people who will experience the greatest change from a welfare program versus the people who have the greatest need. It's hard to decide which one is necessarily a better program if one emphasizes one versus the other. So the basic approach that this paper is going to take is we're going to enter this discussion, but we're not going to try to say necessarily we're not going to try to make that apples and oranges trade-off. What we're just going to do is we're going to observe that governments are already making these trade-offs in their policy designs, that any welfare program is implicitly already making these trade-offs. And so what we're going to present here is a way of using data science and machine learning to infer the effective valuations in policy designs. So the basic intuition is if you have a welfare program that's mostly going to poor people, you could infer that the government is putting higher weight on the poor, and that this program is just similarly effective for all groups. However, you would get a similar allocation if the government didn't actually put any extra weight on the poor, but it just believed that the poor would benefit much more from a welfare program. And finally, the government could actually care more about helping the wealthy, but their relative benefit is just so much steeper for the poor that the effective allocation leads to a higher priority on people with low income. And so the basic framework that we're going to do with this paper is we're going to say that if you have, in government programs right now, we actually already have enough information to observe the leftmost column, which is the allocation, and the rightmost column, which is who's benefiting the most from a given program. And we're going to say that this gives us enough information to back out the middle column. So we're going to be able to take this allocation and estimates of the marginal impacts of the program, and we're going to be able to infer who's being implicitly valued in the program design and what outcomes are being implicitly valued as well. So we're going to apply this to make it a little more concrete. We're going to apply this to Mexico's flagship anti-poverty program, Progresa. And so the first thing we're going to do is we're going to use the latest machine learning methods to recover heterogeneous treatment effects. That's a large part of why we're entering the literature now, is because recent advances in machine learning have made it newly possible to recover heterogeneity in treatment with really detailed precision. Then we're going to look at who receives this welfare program. And we're going to back out which types of households are being prioritized and also what types of outcomes are being prioritized. Because the progressive program was sort of holistically trying to improve education outcomes, health outcomes, and consumption among impoverished groups. And we're going to say which ones are effectively being given more weight. And then once we have that framework established, we're actually going to be able to use this sort of stable setting to make some of those tricky apples to oranges comparisons. So we're going to be able to say, we're going to be able to compare two different allocations and show how two different ways of designing this policy effectively prioritize different groups or different outcomes. And then similarly, we're going to say, use this framework to say, if we believe that the government should be giving greater priority to one group or the other, this framework can be used to redesign the allocation to better reflect those values. So the basic model that we're going to use here is standard in the economics literature. We're going to be thinking of social welfare as a sum of utilities. Specifically, we're going to be thinking of a weighted sum where there's certain households are given more weight depending on this function mu, and it also depends on their outcomes v here. So the basic utility of providing a program is going to, of providing this welfare program is going to be a summation of the weights on different outcome priorities and the outcomes that each household has. This would be consumption or whether the children are healthy, whether they're going to school, as well as just a base value of providing the program, irrespective of whether it's effective. And so with this sort of setup, we're able to say that the welfare impact of giving a program to a household is going to be the welfare weight on that household times the weighted sum over the impacts over different outcomes. And so we're going to once we have this sort of weighted summation framework, we can make just a small assumption that we're getting Gumbel errors, and we can use ordinal logit to back out the weights that we want to infer. And the only assumption we really need is to say that if a household is getting the program or is more highly ranked in priority than another household, it must be that the government is, that the weighted sum of utilities for giving this program to the higher priority household is larger than the weighted sum of utilities for giving it to the lower ranked household. And that's the chunkiest bit of the presentation. So hopefully you guys are able to bear with me there. And now we're going to get to the concrete part of the application to Progressa. Progressa, for those of you who don't know, is Mexico's kind of most prominent anti-poverty program. And economists really love to study it because it was implemented in the 90s according to a randomized controlled trial. They staggered the rollout of this program to different villages in Mexico. And those that received the program later were control villages. Those that received them earlier were treatment. And so you can back out really cleanly estimates of the impacts of this program for different households. And earlier work has already noted that there's significant heterogeneity in the impact of this program across households. Also, it was targeted to poor households according to a poverty index. So that's going to be our measure of the priority ranking over households. So what we're going to do is we're going to take these, we're going to estimate heterogeneous impacts of this program, and then we're going to infer the implied priorities that are implicit in the design of this program based on who's getting the program and how effective it is for different households. And then we're going to take the framework and evaluate other ways that it could have been designed to better target certain types of household and what the implications would have been. So just to give you guys kind of like a benchmark of where our model's contribution is coming in, if you weren't using our framework, but we're just trying to say, what is the correlation between different types of households and whether or not they're getting prioritized in this priority ranking, you could basically perform an ordinal logit on household covariates for this poverty score. And you would find that indigenous households are getting higher priority, poor households are also getting higher priority, and households with more children are getting higher priority. But you wouldn't have any information on whether this is because the government is intrinsically valuing helping these households, or the program is actually more effective for certain types of these households. So now we're going to use our method to basically decompose that ranking. So first, we're going to estimate heterogeneous treatment effects. We use causal forest, which is a method from Wager and Athey. We find significant heterogeneity across a number of different dimensions. We're going to be looking at household consumption, the number of sick days that children report having as a measure of sort of household health, and then the number of days that children report missing school as a measure of sort of education outcomes. And so you can see that sick days and missing school are bads. So the fact that there's an average negative effect means the program is helping. Causal forest is a little tricky to communicate. It's sort of one of those black box machine learning methods that doesn't exactly, not as opaque as other methods, but it's hard to break down exactly the coefficient values, but we can say that it's placing especially high importance weight on income and household size, as well as head age. And so now we're going to present where our method. So we've taken these heterogeneous impacts, we've taken this program allocation, and now we're going to estimate using ordinal logit the welfare weights across households and the impact weights over outcomes. And just at first glance, we can see pretty clearly what our method is doing. So the government is giving higher priority to indigenous and lower income households, but a lot of that priority is captured by the fact that this welfare program is already more effective for poorer households and indigenous households. And so the fact that the government is placing a higher ranking on these types of households reflects both phenomena, both that there's a greater intrinsic ranking and the fact that we see higher impacts of giving this program to these types of households. The standard errors here are computed with like a two-step bootstrapping procedure. And so we don't have we aren't able to estimate this with a great deal of precision, especially for the impact weights, but we do see significant effects for income and for the number of children in a household. So we see that the government is really prioritizing households with a lot of kids and poorer households. Our impact weights are really noisy. This is like a slightly data hungry method as it stands. And given the sample size, we're not able to estimate this with precision, but we do find confidence intervals that contain standard estimates from the literature. We've normalized here consumption to be 1, but we do find significant impact weights on consumption here. So we find the government is significantly prioritizing helping people in consumption, but are unable to make strong claims for the other outcomes. And next, we're able to then use this framework to basically evaluate when the government in 2003 changed their priority ranking, we can break down how this priority ranking changed the implicit valuation over different types of households and different types of outcomes. And in particular, we can see that the 2003 priority ranking seems to have increased the priority on indigenous status, but gave less priority to households' poverty status. Similarly, we see moderately more weight on schooling and health impacts, but again, it's very noisy here. And then so finally, in the last step of our procedure, we can take our framework and instead of taking it as given, because this isn't like, we're not making normative claims that this is how it should be, we're basically trying to use this as an observational tool to saying this is what's effectively being enacted. And so if we were a policymaker and we found these valuation estimates and decided that they didn't reflect how we wanted the program to be designed, we could then plug in different values and redesign our allocation ranking to better reflect what we want to see. So here we show that you could redesign it so that there's equal weight across all households, or so that households are just prioritizing poverty. And you can see in this bottom row is basically we then perform we observe the correlations of the final allocation with different outcomes, and we can see that if you just weight equally across all households, you'll be taking away all the priority that's being given to impoverished households. So this welfare weight on poverty is really important to the way the program is prioritizing poorer households. But if you just wanted to prioritize poverty, you could find a much more strongly correlated allocation to design. Similarly, if since our impact weights are very imprecisely estimated, you could plug in estimates from the literature. Here we take estimates from other studies about the peso valuation of child sick days and child's education. And we build other allocations that would reflect these impact weights. And similarly, you can go through and decide if you only wanted to target a program to prioritize certain types of outcomes, you could redesign it so that it only prioritized consumption, education, or health. Yeah, and that's our method in a nutshell. Is we've basically developed this method to infer the effective prioritizations over households and outcomes that are embodied in program designs. We present how this method could be used to audit existing policies to show who's being given priority, and then also to realign them after the fact to better realign stated objectives with the final allocations and actual effects of the program's targeting procedures. Great, thank you so much.
I have a question.
Yes.
So to what extent was this program rolled out sort of intentionally with those ideas in mind? Like you mentioned that it was rolled out to a certain extent randomly. Was that with these outcomes in mind, or are these things that you've kind of worked out backwards?
Yeah, I think I would say that the government was most explicitly prioritizing health and schooling. If you look at how they were actually, because it's a conditional cash transfer program, and the conditions were that you needed the school's, I want to say, principal to verify that your child was was attending classes regularly, and you had you needed the child's doctor to be verifying that you were making regular doctor visits, and so I think consumption was sort of I would say of the three, consumption was probably not explicitly targeted, but it's sort of like a fairly short line to draw, because they were then giving large payments to households for performing these actions of regularly going to school and regularly going to doctor's visits. But that's definitely sort of like an important, there's a lot of important decisions that the researcher is going to be making in using this tool and evaluating and deciding which outcomes to include is definitely one of those like first order important decisions. Similarly, you'll notice that like we only look at kind of restricted subset of attributes for each household, and those were sort of we restrict that group largely just because we don't have the sample size to estimate weights over many more dimensions. But that's again something that will be kind of an important researcher decision to make sure that you're evaluating over outcomes that reflect what the government is actually targeting to target, and over dimensions that the government is actually trying to target over. So I'd say that that's a great question, and it's definitely we don't introduce here like a data-based way of figuring that out, but we trust the sort of in application that there will be that you will be able to prudently build these sets of outcomes and covariates. Yeah.
Any other question?
Hi, Samson. I'm just curious. What is your reasoning behind the selection of causal forest? Why do you choose it? I mean, instead of other machine learning techniques?
Yeah, so we actually, we have explored other methods. Largely, causal forest, I think has been shown to be especially well suited for finding like heterogeneous treatment impacts in sort of these like RCT settings where you have treatment and control groups that are like easily defined. But it's perfectly adaptable to any other situation or any other tool you would plug in there to estimate heterogeneity of impacts. We're basically just kind of presenting causal forests as kind of an example in the same way that we're presenting Progressa as an example. But we have explored using like Lasso, OLS, and a number of just kind of basic off-the-shelf regression methods. And then if you wanted to get fancier, you could definitely go wild, building the best possible estimates of heterogeneity. But yeah, that's a great question.
Do you think that there would be any tool from deep learning that could help you in this problem in particular?
Yeah, I would say that depends on your application. I think as it stands, this method is already fairly data hungry, and I would worry that deep learning would be more data hungry than sort of random forest-based method. So if you were in a really data-rich environment, I would imagine that deep learning could absolutely improve your estimates. I think in our application, we have about like a sample of around 10,000. And so causal forest seems sort of like a more prudent approach in terms of just our data availability. But yeah, I would, that'd be a really fun avenue to explore. I think that could absolutely improve the applications wherever that would be possible.
Thank you.
Yeah.
I have a question. Thank you for the presentation. It was very nice, and I'm very familiar with Progressa. But I just wondered to what extent the characteristics of the population in itself affected the results that you reported with this method. And this is because you stated that the program seemed to prioritize indigenous people and household poverty and number of children in a household. And well, this is actually what the program was targeting, right? It was targeting this set of the population, but more importantly is that the Mexican population is highly comprised by indigenous people. So I don't know to what extent the breakdown of your results could actually conflate into just one big indicator, like all of them are just, I feel like they're telling us the same thing they're telling us different things about one result. Because something that will be I think much more interesting to see is how the program operated, for instance, in populations, indigenous populations in rural areas, that this is where the poverty levels are higher, and how would the program behave, or how it operated in the same population, or population with the same characteristics in metropolitan areas. I think maybe that will bring a little bit more nuance to the results.
Great. Yeah, that's great feedback. I think to your point, I think the fact that we are unable to sort of find precise, like our standard errors are quite large, especially on the covariates over indigenous status. And I would say that that's probably a result, as you were saying, of maybe limited variation within the sample to identify the precise effects. It does seem like there is enough variation in the sample to identify precise effects on income levels, but I think that's a great point. And absolutely, we'll definitely explore the rural urban divide. That's great feedback. Thank you. Yeah.
Okay, so if there are not more questions for Samson, I will thank him again for his interesting talk, and then we will pass to Myra.
Thank you.
Sorry, give me a second. you all see my slides, right?
Yeah, but they are not, yeah, now it's better.
Okay. Okay, so
Well, before that, I should
oh,
introduce.
sorry, yeah, thank you.
Okay. So the next talk is by Mayra Morales. Mayra is a postdoctoral research associate at the University of Manchester. Her broad research interests include questions around science, technology, and innovation, such as research practices, research quality, and policy evaluation. Her PhD thesis, in her PhD thesis, Mayra explored the effects of Mexico's scholarship program. Mayra obtained her master's degree from the Metropolitan Autonomous University of Mexico. Today, she is going to tell us about her work on Let's Talk Connecting STNI Studies with Data Science.
Thank you. Well, this is the structure of my presentation today. And basically what I'm bringing today to you is, I'll say this is sort of a problem, something that emerged when I conducted a literature review, where I noticed that the practices and research in social sciences are shifting, are changing. And this is in part due to the trend or that to the huge amount of data, of digital data that we have nowadays, and also to the increasing and numerous tools that we have now, from free software to paid software. So I want to explain a little bit where I'm coming from. I have to say that being a social scientist at this moment is really is fantastic. It's fun and interesting. It's really exciting because now we have access to data that before it was simply not easy to have, or it was not existent or expensive to collect. Now we can find and explore questions and solutions to problems that existed before with new approaches, but also there are numerous new problems that are emerging nowadays. The sources of information that we have now, well, that's why I wanted to bring this image. We are generating, I mean, I don't have a word for that, but humongous amounts of data every minute. And as a social scientist, I've seen numerous studies, very interesting, using social media, but also using software development platforms. There was a very interesting study where they show how developers at GitHub are like self-organizing themselves. It's very interesting research, but I won't delve into that. Well, that's one of the benefits. There are also some risks, and that is what brings me or drove me to this presentation. And well, there are many risks, and we can just take this presentation talking and having a list of all of them. But the most common that the research results that we have may influence decisions about voting decisions, attitudes towards migration and vaccines. And the one that concerns me the most is the lack of reflexivity that as researchers we can have. And this comes down to the fact that sometimes we adopt methodologies or we use data without questioning the origins of this data. I mean, we don't know sometimes who created this data, what were the rationales behind this data, and what the data was actually created for, what we're using it. So this always leaves an open question as to whether the results or the findings that we are reporting actually can actually be reliable. Okay. And well, the image that I brought there is a very good illustration of the benefits and the risks that we face nowadays with the advances in computer sciences and mathematics, right? That on the one hand, they have facilitator of life, but those can also influence and affect the practices that we have as researchers. So again, is for me, the lack of reflexivity is what worries me the most. And this worries me because we can oversimplify how data sciences and social sciences connect. And this oversimplification can have severe implications, for instance, in in policy making, sorry. There was a case that I found it interesting. There was a program that was implemented, uh, I think it was in Arizona State, where they're using algorithms to decide on the years of sentence of prisoners. And what they found is that, well, this machine has some bias towards a particular racial group. So there are always these kind of pitfalls that we find that we have when we work with machines. And now to give some context as to where I stand, well, I'm from Science and Technology Studies. This is I'll say a very new field. Only up to the 60s, it was not considered a field as a research field as such. And well, it is economics, the discipline that gives origin to it, and also sociology of science. And just to illustrate how diverse this field is that mainly is led by economics. Around, let me see, more than 50% of the people in the field come from economics, and then from engineering. An interesting comment here is that I've seen, and there are studies on this, is that economists and people from the natural sciences that come to science and technology studies can have a better career in the field. It might be because of the use of some preferred methodologies, we don't know. But in case you want to jump in over here, yeah, you'll have a good career. Other people in the field come from sociology, psychology, policy, and the health sciences. About the structure of the knowledge in the field, again, I love this network because it shows it has the same pattern as the figure before, is that we have a huge network of people with more interdisciplinary interests, but also we have the network of economics over here, which tend to be the more quantitative ones, and they really don't like joining the people over here on this side of the network. Well, these are interesting patterns that have already been explored and documented in different papers. So I won't dwell into that. I'm gonna talk now about the practice, and the practice is literature reviews. I'm sure that you are all familiar with what a literature review is. But for me, it sparked a lot of inquiries as to how we are changing, or we are orienting our research interest because of how easy it has become to do a literature review thanks to the facility and to the power of computers. But mostly we tend to do literature reviews because we want to find a topic that is specific to interesting research questions. And as we just saw in the network the previous slide, this is a field where knowledge is really interconnected. So sometimes developing research questions requires, I'm talking as my experience as a PhD, requires for us to explore a huge amount of literature. And well, we need to find a specific topic that, that gets our attention and that gets our interest. So that's why we do literature reviews. And also because at the end, we want to emphasize where our contribution to theory sits. Another reason why we do literature reviews is because this has become, this is a must in, at least in business schools, is all PhDs are, I wouldn't say required, because no, I mean, we're not required to, but we are encouraged to draft a literature review that can be publishable, regardless of whether this is going to be part of your thesis or not. Most of the times we are encouraged to do this. Okay, and because literature reviews can really be time consuming, the adoption of technologies is really increasing. I did a quite a quick overview or of how the journals are behaving, and most of the reviews that I read were using some kind of software to gather, analyze, and to collect the data. Okay. Okay, this is just the trend this is how many literature reviews are annually published in 3 of the main or the most important journals in the field. I want to clarify that I hazard to say that the pattern will be the same if I had used a different combinations of words and if I had extended the search to other more topic specific journals, but the numbers will be probably more. But I just wanted to give a glimpse of how important in this field literature reviews are becoming. Okay. Well, literature reviews, we're not inventing the wheel. These are, very well standardized process. We adopted it from the health sciences. And yeah, when we do a literature review, we all follow these different steps. And after showing you this, I want to tell you how I did mine and why I'm here trying to tap into the opportunity of having experts in data sciences and computer sciences so that maybe we can think about co-developing more comprehensive theories where not a field overpowers the other, but where we try to understand what drives our inquiries. Okay, I follow the exact same process that I just showed before. I cleaned the data. I had initially over 500 documents. It included policy documents, included grade literature and academic literature. And I went to, because I found data so interesting at the moment that I wanted to make the most out of the opportunity that I was having collecting such a huge amount of data on just one topic. So I tried using software. I consulted with colleagues as to what they thought was best. I tried NVivo and Atlas D. These are quite popular in qualitative research. I also tried some R packages, but I was left with the feeling that the analysis these programs were making were not capturing they were not capturing the essence of the knowledge that was being produced in the documents. So I went old school, and yeah, I used a spreadsheet. At the beginning, I was just trying to see how I could organize data. What I did is to read from start to end each of the documents. After cleaning the data, it was over 300 documents, 345, I think. And first I wanted to, to put all the relevant elements of each document here. And this is where the first column is. But obviously this doesn't say anything. I couldn't just, draft a report saying, okay, this is what the papers are telling us. Mind you, there are some literature reviews that are quite descriptive. They just tell you how many papers they found and what each paper contained. And there is value in that sometimes because it saves you a lot of time from reading a whole body of literature. After having those huge chunks. I broke it into smaller chunks, more workable chunks, I'll say, of data, and started to color code each entry in the spreadsheet. And the reason for color coding was that I started to see a few patterns emerging after going through the data or through the entries several times. And after that, and reading again, I saw what was the main concept behind each of the chunks of information. And well, the spreadsheet started to see a little bit more cleaner, more simple to read, and with more potential to draw important or relevant conclusions to the field. And well, the final table that the table that I ended with is this one. I can say that it was a pretty intensive work in terms of yes, working with that in terms of the empirics, but also in terms of the intellectual work and all the learning that it implied. And so this gave us a result, a paper that we just published in last year. And this beautiful table over here, well, the mother, this table is a not good looking table over here is the mother of this one over here. And it's just one of the tables that we produced. Okay. And what something that I enjoyed about the exercise, and after the comments from the reviewers and comments from people in the community, is that they seem to really enjoy the work. We normally get comments on the work, stating that this is not the usual literature review that only shows some graphs or the structure of knowledge or how one paper or one author connects to the other, but that it contributed to theory. It contributed to better understand how the topic, in this case, was research evaluation, how the topic is evolving, what are the priorities in terms of policy making, what are the methods that are driving this topic, among other insights that the paper provided. Okay, so what I learned with this exercise and what ignited my questions, I'm going to show you my questions in a bit, is that I noticed in different, because I attended a few events and I kind of organized some informal talks with colleagues. And yeah, I became aware about how little we actually understand how computer-led tools work. These are a black box to us. I mean, some of us in the field are quite good. Okay, they have a backgrounds on mathematics or engineering, and they have a better insight as to how these tools work. But most of us just simply use them without questioning what they do, how they do things. And this has created some questions already in philosophy of science, and this is the question of a lack of truth, and that's that we don't know whether we are using data or making data say or do things for which this data was not meant to do. We might be misusing data and methods as well. Something else that is starting to emerge as a practice in the field is that we are adopting these tools and these methods as a way of legitimizing what we do. I remember, and I documented almost all the comments that I gathered in these events, is that people would tend to see as more valid and credible a literature review if the author had used some kind of software to analyze it than if it had just been done by a human. And also, and I would like to hear your comments on this, there might be a disconnect at this moment, but it can be the opportunity to connect both disciplines, is that maybe computer scientists or experts on data, their understanding of social sciences might not be as accurate. Maybe they think that the way the problems that we encounter and the way we approach them is generalizable, and well, this is not this is actually never the truth in social sciences. So yeah, this per and kind of yeah, I would wonder how we can bring this how can we work together to make and co-develop methods that can actually contribute to both disciplines. Well, these are the questions. Some of, well, both you have already been listening throughout the presentation. And yeah, basically it's about how can we work together, you as experts in computer and data sciences and us as social scientists. And that's it from me.
All right, thank you, Meira. Are there any questions for Meira?
I have one. I was wondering to what extent you see like this kind of work and the changes that you want to see. Do you want to see them within your field, which is this interdisciplinary field, or are you hoping to spread things even further? Like, do you think there's things that these individual disciplines need to learn from this and adopt within their work, or is there kind of a unique approach that this interdisciplinary field of that you're in needs to take?
I mean, because the field is interdisciplinary, if the field if the better of the understanding we have in the field about digital methods and digital data, the more also other social sciences will start, to question their own practices. Yeah.
Are there any other questions?
Yeah, I guess I have a quick question. I wonder like how much, because this feels like it also relates kind of to the pedagogy of how we prepare researchers. And I guess I'm interested in like, to what extent do you see this as something we need to change in, because like, especially sort of like for people like using tools that they don't necessarily understand the inner workings of, do you think that there should be like a stronger kind of methodological pedagogy for disciplines that might be using tools from other places, or do you see that as sort of like a sort of a researcher by researcher thing, like if you're engaging with a certain tool to sort of try and really understand the inner workings of it?
Yeah, it's a case by case kind of thing. But I think that what worries me at the moment is that I've seen that we are adopting, that digitalization of everything more as a fad rather than as something that can contribute to the knowledge that we bring to theory and to the understanding of society. And it's a case by case, because every scientist has its own not only background but also interest, in the sense that we'll have to go into philosophy of science here, but let's just say that some people might think that, or people might believe that, for instance, quantitative methods are telling the truth or represent the truth better than qualitative methods, whereas others might say that this is not necessarily true. So it is about what people learn during their training, but it's also about what the field accepts as valid truth. I don't know if that makes sense.
No, that makes a lot of sense to me. I think that's a lot of like especially like coming from economics, like economics has had like this reckoning in the most recent years with a lot of bias within our own discipline. And a lot of that came from this like the way that discussions used to go about sort of, I can imagine an economist having a gender bias discussion in the mid 2000s where they would say, we don't have strong evidence that this is like causing these things. And that would be taken at face value as sort of being like, we're going to be data biased. We're going to be data based and say maybe sexism isn't real, because there weren't studies at that point and sort of like data-based methodologies that were producing knowledge within the frameworks that they were prepared to accept as like ground truths, and it clearly severely limited a lot of ways to actually address real and pressing issues in the discipline, and more broadly in society as a whole.
It also, other thing is that polarizes scientists, one view more towards adopting quantitative methods, that in quantitative methods involving data sciences and others. And then we would disregard the value of other methodologies. Because after all, we're not a field that creates methodology, we are a field that creates theory. So that's why I think that is important to speak about this. Yeah, thank you.
All right, thank you very much, Mayra. And if there are no more questions, I would like to ask Koiko to start his talk. Thank you again.
Yeah, thank you both, Samson and Myra, for the great talks. I think that also my subject matter might be a fitting sequel to what was just discussed. But
while you are fixing your slides, perhaps I just read your short bio. Actually, we have to wait 3 more minutes because you start at 3.
Okay. But can everybody see my slides, the title slide?
Everything is relative.
Naming papers and naming projects is maybe the best part.
I can relatively assert that I see your slides well.
Perfect.
All right. We now have Kwaku Kwerger. Sorry. We now have Kwaku Kwerger Agre, who is going to tell us about his research. Kwaku is a second-year PhD student in computer science at Brown University in the Encrypted Systems Lab, where he studies bias, audits, and verifiability in machine learning under advice of Professor Sunny Kamara. He also worked closely with Professor Sarah M. Brown at University of Rhode Island. His work mostly falls at the intersection of machine learning and theory and works to critique data-driven technological solutionism by asking questions like, why does it make sense to use machine learning, and when can the technology do harm? Today, he is going to tell us about his work on fair comparison with optimal transport. So please.
Thank you so much for the introduction. I think that's the first time I've ever been introduced. So that's why I was giggling a little bit. But yes, today I'll be talking about understanding fairness with optimal transport. A couple things to keep in mind throughout the talk. It's unfortunately a bit long-winded, but I know it's a Friday and everyone's trying to move on with their workday, so I'll try and keep it brief. And then another thing is that one of the themes that goes on throughout my slides is that I think kind of the way that computer scientists approach a lot of fairness issues lacks kind of sufficient nuance. And I think that I tried to situate the work somewhat between the kind of social science perspective that we just heard about with some of the more rigor that's provided by a technical discipline like CS. But without any more kind of exposition, the way I'd like to kind of motivate my research is by talking about the bail bond system. And so what you're looking at is a picture of a bail bonds building. I'm guessing this is somewhere in California, I'm not sure. But the way bail bonds work is that if you get convicted of if you get arrested for some crime, prior to awaiting trial, you will go to a judge and the judge will determine whether or not you should await this trial, you know, out in the public or in jail, right? And so in the situation that the judge decides to keep you in jail, you can be released on what's called bail. And if someone pays enough money to get you out of jail, now you get to go walk free. But the issue is that a lot of policing, we know, disproportionately affects low-income communities. And so bail really becomes like a, you know, get out of jail free card for people who can afford it. And for low-income people who cannot afford it, it becomes difficult to pay their bail. And so as a result, we have establishments like this, these kind of short-term lenders called bail bonders, where say your bail is set at $10,000, they'll collect 10%, so $1,000, and then some collateral, you know, your house, your dog, your Netflix account, whatever it may be. And then they keep that collateral until the court case. And in the situation you comply with all the legal proceedings, then they'll give you back your collateral, keep your money. And so then you've only had to pay a fraction of your bail in order to get out. But in the situation that you don't, they keep the collateral, and now you've gone to jail and you've also lost some of your things, right? But a lot of people recognize that this isn't just. And so recently in California, Proposition 25 was put on the ballot, which basically suggested replacing the bail bond system. This is kind of taken from the California Voters website, decided to try and replace the bail bond system with automated critical risk assessment tools, right? And so what we wanted to do was have people be assessed on whether or not they should be released based on a kind of automated data-driven tool determining how risky they were. But as we recently kind of heard about, and as these things kind of become more common knowledge, we know that a lot of these risk assessment tools are prone to exhibiting biases that we would like to prevent, right? And so one of the most popular examples of these risk assessment tools is a tool called Compass, released by this company called Northpoint. And so what we see on the screen here is some of the individuals who are classified under Compass. So what happened is that you would go through and they had a bunch of surveys asking kind of strange questions, and they would take you through a series of interviews. And what they wanted to do was create a model to determine how risky you were, right? But unfortunately, there was a lot of racial bias that was embedded into the model. And so if we look at the kind of group of people on the left, we see that this Vernon Prater fellow has 2 armed robberies, 1 attempted robbery. But after a 2-year period following his arrest, because what we're trying to predict is how risky you are after being arrested, there was 1 grand theft, right? And so he actually was someone who should have been classified as risky because he reoffended. Borden, on the other hand, was someone with 4 juvenile misdemeanors, but received a much higher risk score despite not actually subsequently committing another crime. And we kind of see the same thing on the right side, where this person who's been accused of domestic violence, aggravated assault, had a risk score of 3, which seems kind of egregious compared to the person to his right who had 1 petty theft and had a risk score of 6, right? And so the difference between these people is the color of their skin. So obviously there's racial bias embedded in the system. And if we look at the distribution of risk scores for each of these groups of people, we see that for the Black defendants, the risk scores are kind of uniformly distributed across the top. Whereas for the white defendants, the scores decrease from right to left. And so in the case of the white defendants, this kind of makes sense, right? We'd assume there'd be more low risk people than there are high risk people, right? The super risky people, the Batman villains, they're not as common as the low risk people. But we don't kind of see the same trend on the left side of the screen for the Black defendants. We see that these scores are uniformly distributed across their scores. And so this is a problem, right? We want to kind of more deeply interrogate what is the structure of this bias that we're observing. How can we understand more about it? And so to do this, we kind of have to turn these issues of fairness, at least that's what the machine learning community calls them, into a kind of like tractable problem where we can do computation and figure out how to make progress. And so that kind of begs the question, how is fairness defined in machine learning contexts? So typically we have 2 notions of fairness. We have fairness that we define in terms of groups like sex, gender, race, and we have fairness that we talk about at the individual level, and I'll kind of give an overview of how those types of definitions are evoked and what their applicability is. And so in the case of group fairness, we have this example where income is on the y-axis, x-axis isn't really that relevant, but the line indicates based on your income, whether or not you are predicted to pay back a loan or whether or not you were to default. And so above the line means I predict you pay back, below the line means I predict you default. And then we also look at the color of the dots, which is kind of the ground truth, what actually happened, right? And so the notion of demographic parity in the notion of demographic parity just kind of stipulates that I have to give out loans to each group at the same rate. And so we see that half of group B and half of group A both received loans, half of the dots are above the lines, right? And so we can understand how in some situations this isn't a sufficient notion of equity, because what if the amount of loan repayment in group A is simply different from the amount of loan repayment in group B? Now we kind of have these 3 uncolored dots, these unshaded dots in group B, who are being classified as reliable loaners when in fact they are not, right? And so this simple kind of intuitive, have everything be the same, regardless of protected attribute, falls a little bit short, right? And so we tried to kind of reform this definition with the following, which is called equal opportunity. And equal opportunity instead looks to equalize the true positive rates. And so we kind of have the same exact situation, but the true positive rate is computed from the number of people who are actually positive, the number of people who repaid a loan, where that would be in the denominator, and then in the numerator would be the number of people who are classified as having paid back a loan, right? So on the left side, 9 of the 12 actually paid back group are above the line. True positive rate is 75%. Same thing on the right-hand side, we also have a 75% true positive rate. But all of these unshaded dots that are above the line are false positives. And so in the process of trying to equalize these true positive rates, now this equal opportunity definition, for example, promotes a higher number of false positives, which isn't great, right? And so we can kind of understand how these flavor of definitions, which are standard practice in computer science literature, kind of fall short at times in different ways, unique to each of the definitions, but they're still insufficient. And so those are kind of just 2 brief examples of group fairness notions. And then we also have the notion of individual fairness, which I'll kind of describe more precisely on the next slide. But this is basically a graphic to show that these 2 dots, if they were people, their similarity in their feature space, how we define them, how we define merit, whatever it may be, should correlate with a similarity in the outcome space. And so if we're looking at GPA as the kind of GPA and maybe SAT score as the X and Y axis in this diagram, these people who are relatively similar in those features should roughly have the same likelihood in college admissions, things of that nature, right? The only issue with individual fairness is that kind of bestowing classifications like merit and similarity metrics over features and outcomes is kind of a non-trivial task, right? And so if I have an ability to kind of determine how people are similar in a perfect way, that kind of reveals that I've gained some additional insight about the problem, which isn't always available to us, right? If we knew a priori how to prevent bias by knowing exactly how to measure similarities between people, what are the meaningful similarities, we wouldn't need to evoke this style of definition. It would kind of be tautologically solved already, right? And so this is kind of the closed form definition of some of these fairness expressions. So demographic parity is the first one, which is kind of just independence between the classification and the protected attribute. Equal opportunity, we introduce a y hat, which is the predicted label. And so if where predicted label is true, then that means the probability of true classification should also be the same across protected groups. And then below individual fairness, this h of x is just kind of a classifier. Basically, the outcomes of the classification should be the same for individuals that are kind of similar, bounded above by their distances in feature space, right? But I kind of felt that through some of our research, we found that these were insufficient for some of the notions we mentioned before. We think that a much more powerful intuition about how to think about fairness is to think about it through example, right? And so if we make the assessment that something is unfair, it's usually by comparison to an ideal that we think is fair. You observe a process go by a couple times, you see a couple samples, you say, I don't think that this should have happened in comparison to the mental model that I have about what should have happened, right? And so through comparing your understanding of fairness in some scenario, you kind of bring your own definition. System planners also bring their own definition, but in being able to kind of enumerate examples of like what fair should have been in the situation, I think it permits more nuance in the situation that you would like to kind of describe what fair means. You know, just give me examples of what it means to be fair instead of giving me an equation. So we'll try and tease more kind of power and mathematical elegance out of that type of intuition. So to introduce some notation, we allow a policy to be a mapping from a feature space X to the space of possible outcomes, kind of O of Y. And so this policy notation can abstract classifiers, which is what's given in the first example, right? A lot of the time in machine learning classification, we'll give probability vectors, as you know. I think you're 65 or 35% likely to have outcome 0 and 65% likely to have outcome 1 as denoted by the f of x1, or you know the probability could be slightly different. Or in the situation in the second example, I have kind of 3 possible outcomes. These could just be assigning 100% possibility to one of the outcomes in the form of kind of like a data set labeling case, right? When you have a data set, all you see is the written down data set. So we assume that that was the kind of observed outcome with 100% probability. And so the intuition is basically if I have these 2 policy functions that are similar to one another, that by regarding the similarities between the 2 of them, I'm able to kind of further understand how they might deviate. And so in the situation that one of my policies represents a fair ideal, if I'm comparing it to a different policy, right? If the second policy is similar to the first policy, then in a kind of transitive way, it is fair. If the second policy is dissimilar to my first policy, which is designated as fair, then that second policy must be unfair with regards to that fixed notion of fairness. And so that kind of comparative intuition is what we rely on throughout the problem. And so now what remains is how can we evoke this notion of similarity over outcomes, and how can we do so in a meaningful way? And so the kind of mathematical tool that we recruited to do this is called optimal transport. And optimal transport is kind of one of my favorite types of mathematics because I find it to be really elegant at describing these types of problems. Basically, what we want to do is figure out a way to translate one distribution of things into another distribution of things. So if we imagine these as like Play-Doh, what's the kind of least expensive way for me to kind of squeeze the distribution on the left into the distribution on the right? And the kind of notion of like the least expensive way, we have flexibility in defining a cost function, right? And so in a traditional Euclidean sense, we could use a norm, but as we'll see later on in the presentation, we can actually use several other distance metrics that are still norms. They're still Euclidean norms, but they're really not over the entire feature space. And so we kind of, one of these issues is that previous types of fairness in this space have tried to only operate using Euclidean norms, but we think that you actually get a lot more expressiveness out of the problem when we think about fairness under multiple axes and allow the definition of multiple types of distance functions. Before I proceed, does anyone have any questions regarding kind of the intuition and problem setup?
I have a question about the way you define fairness. So
Yes.
you are basically saying that if like the policy is acting the same to the 2 different groups, it's fair. But I guess, for example, like if you say all the people, like if it's a policy that, what if it's a policy that is unfair to everybody? Like you are not comparing to different populations. Like let's say everybody goes to jail if they say something that
Sure.
cannot be fair either.
I think the thing is that you have to meaningfully instantiate a definition of fairness. I think that the thing that's missing kind of from this instantiation is that it doesn't require there to be a fixed definition of fairness. And so what it means to be fair in that scenario is a parameter. So in the situation that we have, you know, some crazy government that does want to put people in jail for a nonsensical reason, if that's what the fair standard is, you should still be able to examine behavior compared to whatever that fair standard should be. And so the reason that we do evoke this comparative notion is so that we can compare 2 things for how similar they are, regardless of what it may be. And so this kind of lists us up from the space of having to fix kind of closed form fair definitions and closer towards a more expressive, nuanced, sample-based approach.
I have a quick question. I was wondering, like, just like looking at this image is striking, and I guess I'm wondering, it seems like this approach would be best applied in places like the one where you presented to us, where you have like a distribution of scores over sort of like 1 to 9, but then sort of within, if you're just looking at like binary outcomes, it would sort of become sort of degenerate to just kind of making sure that the average is matched.
Sure.
And so, to what extent do you anticipate that this would be like? Do you think that this would still be the like best way to proceed if you just had like 0-1 outcomes for everybody, so that you're just trying to like match means basically, or do you think that this is also it would almost seem like you could make an argument that providing a greater, like a more finely tuned scaling of your outcomes is like would be a precursor to being able to ensure fairness in these ways?
Sure. So one of the things that we kind of show later on is that in a lot of like predictive machine learning tests, we get a classification vector for what I think is going to happen, right? And unfortunately, we have to make approximations somewhere, right? If I get a data set and I'm trying to figure out how far my outcomes deviate from a notion of fairness that's in terms of the data set, which is just observed what happened, what didn't happen, I don't really have these probabilities like you described, right? And so the kind of tricky thing is that we still get meaningful solutions out of the framework I'll describe when we do consider the binary outcome. But the other,
so you kind of like, you go one step earlier so you can find a little bit more continuity of the, like
yes,
before it gets translated. Okay, that's cool.
Right.
Okay,
if
cool.
I throw things into a logistic regression, now I'm going to have this is 23% this and 70
Sure, yeah.
percent this, and now that kind of comparison to maybe a binary labeling case is a bit more meaningful than just 1-0 versus 0, right?
Okay, great. That totally answers my question. Thanks.
Perfect. And so the way that we kind of think about optimal transport is in, as I described, kind of the least expensive way to change one distribution into another. In this situation, we'll be thinking about distributions over outcomes. And so the outcomes themselves, we think of kind of distributional objects. They're describing tendencies of what's likely to happen, but we consider another distribution kind of on top of those tendencies. And so the expression that you're seeing here is basically that we're looking for an object called a coupling, which describes how certain parts of the first distribution are going to be shifted into certain parts of the second distribution. I'll kind of zoom past these specifics because I don't think for the purpose of the intuition they're too crucial, but basically we have a cost function that we're defining with respect to this kind of probabilistic measure over our variables x1 and x2. And so the set of joint distributions that we're looking to minimize over, and I'll kind of make this joint distribution notion clear in the next slide. It's a bunch of gobbledygook now, is the set of couplings between the two distributions we're concerned about, so the fair and unfair, right? And so the transport plan basically describes a recipe for how I can get this one group of things to look like this other group of things. And so in the context of the most popular example evoked in optimal transport, we think of factories and mines. So how am I doing on time? Okay. We think of factories and mines. And so it's kind of, if I have a bunch of coal and some mines, what's the cheapest way for me to get it to these factories? We see the plan on the left. If we allow purple to be mines and maybe orange to be factories, there's a lot of traveling that doesn't need to happen. If we look at the plan on the right now, the mine is going to the closest factory, and that's kind of the cheapest way. And so if we think about this intuition with regards to our fairness example, if I have one set of distribution of outcomes, how is it that I can shift it to this other set of distributions of outcomes produced by a second policy so that those two things are the same? The deviation between the two of them is kind of like a sufficient measure for bias, right? Like what's the kind of least expensive way I can shift this one group of things into the second group of things, right? And so in order to measure that, we use the Wasserstein distance, which as we see kind of leverages our, is my mouse not showing up? That's a shame. Okay, under the infimum in the first term, we kind of have our optimal coupling that we're looking for. And so it operates on the same machinery. However, the cost function, which was a C before, has now shifted to a D. So now we're kind of thinking about Euclidean norms to this P exponent, but in most of our cases, we'll think about the Wasserstein 1 distance. And so there's really nothing special about this expression, right? It's just kind of a minimum expected value over couplings where the probabilities are given by the joint distribution via the coupling, and our cost is given by the distance function. And so in the optimal transport situation, one of the beautiful things about the optimal transport theory is that you still get good results when we define things discretely. And so in the last slide, we kind of assumed we had continuous distributions. All of this is basically to say I can approximate marginal distributions in a discrete sense using observations from samples. There are some results which basically show that we get decent convergence to the true Wasserstein distance using only samples from the two distributions that we're trying to compare. In the context of this problem, what that means is that I can basically take a group of samples, x1 and x2, say that x1 is fair, x2 is unfair, look at their outcomes and compare them, and I'll still get a pretty good indication of what's going on. So now the optimal transport problem, which is described below, gives us a measurement of how much the two distributions of outcomes deviate, but now the optimal transport mapping tells us exactly how they deviate. So for free, from this optimal transport framework, we get a measurement, and then we also get a kind of recipe explaining to us what is being measured in our measurement. And so in the context of our problem, this is basically what we did. We approximated two empirical distributions for two policies, F1 and F2, for two samples A and B, and basically using the same kind of distributional logic that I described in the first slide. We use the cost function, which is described in the last line of the slide here, which is just the difference between the outcomes produced by, you know, some policy with regards to person A, some policy with regards to person B. The thing I'd like to emphasize in this slide is that I can do comparisons between two groups that are different. And that's kind of another part of this framework, which is really powerful. Sensibly, you wouldn't want to compare two completely disparate populations, but in the situation that you have two groups, maybe one school versus another school, or maybe one bank versus another bank, if you have sensible knowledge that the two domains are similar enough, then the logic of this comparison still holds, because we can assume that their consumers, their applicants are maybe from the same distribution, and so the comparison is valid. And so to make all of this concrete, no more math, we have two schools, school A with GPAs and school B with GPAs. We have, 4.0, 3.5, 2.0, and then the school B GPAs. So what I'm going to do is apply a policy, which is an admissions criteria, right? And so now this is going to give me a distribution via some predictor, right, of how likely these people are to get admitted, right? And so the school A outcomes are listed there and the school B outcomes are listed there. So we can see that for somebody with a 3.5 compared to a 3.0, the person with a 3.0 at school B is a lot more likely to get in with a 3.5 at school A, right? So say we consider that as an instance of some type of discrimination, or at least dissimilarity between the two policies. What the optimal transport map gives us is this matrix on the right, and it shows us how much of the similarity from group A and group B in terms of the outcomes can be related to similarity in the other group. And so we see that the person F1, and sorry, it's a little bit blurry along the rows and the columns, but we see that person F1 having policy F1 maps their similarity the most to the person with the 4.0 GPA in the other school, right? That makes sense. The remainder of the mass, because it can't all be mapped because we have some kind of capacity constraints on this matrix, is mapped to the next best person, right? And so through kind of following this logic, we see, okay, person A wants to be like persons B1 and B2 in school B. Person A2 wants to be like persons B2 and B3 in school B, right? And so by comparing the differences in their outcome space, we can relate that to differences on the income space and kind of get meaningful comparisons between the two things. And so evoking this optimal transport mapping, we can define bias due onto an individual, which is basically the sum of the distances in the feature space from the people who are mapped as similar to you in the outcome space. So that's kind of what this equation describes, the expected value over the coupling when we fix some individual A. But again, the kind of specifics aren't too important. But we can also look at a group bias metric where we divide our input space into discrete subgroups. And now we can add up all of the individual bias terms for everybody in some subgroup, and then think about how much the bias is affecting them as a group, as long as you normalize it adequately, right? And so the reason why this is really powerful is we've moved past protected group assumptions. We remember in the first slide, I was kind of looking at two columns, A and B. I could only do A equals 0 and A equals 1. Now we're allowed to flexibly define subgroups however we'd like. And so this allows us to consider intersectional identities. This allows us to consider subsets of a feature space. Maybe I'm not only considered about people with an income above, 70,000 that apply to the loan, but also those people who have several dependents, maybe more than their counterparts who make less than them, right? And so I can flexibly define groups and observe a structure of bias that's meaningful to me. And then the final thing is that using the same formulation and in the kind of comparative way I was showing, everyone's bias is a result of someone else who was achieving outcomes similar to them, but had vastly different features. And so we can decompose this group bias score based on the other subgroups that have been defined. And so this also allows you to, within the framework itself, describe and think about how other people are being treated similarly to you, and what effect other groups kind of have on the bias that's being observed by your group. So some graphs and some experiments. We consider two schools, school A and school B. In school A, all of the students get accepted with probability 25%. In school B, the top 25% of students by GPA get accepted always. The bottom 75 are automatically rejected, right? And so this means that the bottom 75% of kids at school A are getting a boost, whereas the bottom 75% of kids at school B are not doing so great. And we could say that the top 25% of kids at school A are benefited compared to their, or at school B, pardon me, are benefited compared to their school A counterparts. But we also see that everyone at school A is kind of having a better time in this admission process in general. So that's what we'll focus on. The important thing to note is that on average, I'm accepting 25% of the students from both schools, right? And so if we look at disparate impacts, which is a measure of demographic parity, one of the fairness notions I had on the first slide, basically, if the two proportions are the same, the numerator and denominator of the fraction, I'm doing great, right? If our disparate impact, if this ratio, so for every 5 accepted kids in school A, there are less than 4 accepted kids in school B, the model admits disparate impact, which is bad. We can think that maybe it's giving preferential treatment to this kids in school A over the kids in school B, right? But if I kind of run this simulation that I described a second ago on this slide multiple times over, I'll see that because there are 25% of the kids from each school getting accepted, that keeping track of the disparate impact measurement for several years of admissions will converge towards the number 1, because via law of large numbers, this ratio is 0.25 over 0.25 every single time with some variability. So from left to right, we can see the disparate impact score in aggregate will converge to 1, which is considered the perfect fair level under disparate impact, because that means everything's equal despite there being obvious structural inequity. If we look at the figure on the right side, which is the Wasserstein distance, we see that for various levels of acceptance rule, you know, I could do a 10%, 90% thing or 25, 75 like I described, we record less bias in the situation as we kind of decrease towards the fairness lower bound, which is the situation where, which is the situation where nobody gets accepted, and that's kind of trivially fair in a sense. And so the first thing that we observe from this is the Wasserstein distance is able to recover some intricacies of bias that disparate impact does not really consider. The next thing that we'll do is go back to our criminal justice example and think about a fair policy and an unfair policy and how that kind of affects the sources of bias that we observe, right? And so basically, I trained 2 logistic regressions on the data set, the criminal justice data set we looked at earlier, 1 using the kind of bias risk score predictions, and 2 using the predictions about what actually happened. Did these people actually recommit a crime, right? And so if we look at the figure on the left, which is comparing these 2 policies, the ground truth policy to the observed policy, we see that a lot of the bias is due to correspondences that we kind of predict based on the example that I gave. A lot of the bias from the black high group relates to similarities in outcomes to people in the white low group. Conversely, a lot of people in the white low group, I'm looking at kind of figure A right now, relates to similarities in outcome over the black high group, right? Which isn't great, because that means these people are achieving similar outcomes based on their race and not on features which they should be held accountable for. So on the right-hand side, what we did was kind of apply a equal opportunity classifier, which is one of the notions of fairness, to try and improve the true positive rates, because that was one of the measurements that was lacking in the scenario. And we see that we've actually recovered a lot more similarity in this kind of equal opportunity case from the white low group to the black high group by implementing this kind of fair improvement. And so what we can see is that if you look just from the ground truth to the predicted now, that there's a lot more correspondence of people being mapped to people of their similar kind of socioeconomic, not socioeconomic, their kind of similar criminal history status, right? And so our framework is in some sense recovering improved fair behavior on the group level, right? And so the next thing that we want to look at is, okay, you're telling me how 2 things are different, but can we make this actionable? So then we went on to explore what's called recourse, which is basically how can I give a recommendation as to how to improve your evaluation in the eyes of the machine learning classifier. And so we looked at a German credit data set. I don't know when it was collected, but it has a bank would give some people, they were assigned good credit. They said, hey, based on your whatever features I collected, you have good credit. Other people have bad credit. And so we consider recourse only for actionable features, like how much you have in your savings account, I'm trying to, let me briefly look at the list of actionable features before I'm telling everybody the wrong stuff. Yeah, we look at savings account and credit history, the number of liable individuals, whether or not you're unemployed, kind of things that are within your control to change at the moment, as opposed to inactionable features, which are really like how much money you're requesting. That's more of a function of the loan processing, and immutable features like your number of dependents or your age or gender or sex. And so we kind of interpolate people in the following way. We look at you as an individual who had bad credit and who that has good credit you were kind of mapped to. So of the good credit people, who was the most similar to you in outcome space, and we try and understand what accounts for those differences in this mapping. And so the important thing to look at when we kind of map these individual bias scores that I described before, and I'm almost done, I apologize for going over time a little bit. But for the individual bias scores, if we look at the graph on the right, for the immutable features, we can see that both of the female groups have a higher individual bias score for their immutable features, which means that for the things that they cannot change, they are kind of being held accountable the most compared to the other groups, right? Which isn't great. But if we look at the figure A on the left-hand side, which is for the actionable features, we see that despite young women being the group of people who was denied credit the most in this situation, it's actually the group of older men who have the most bias as the result of their actionable features, right? And so that means if they have the most bias as the result of their actionable features, they have the biggest opportunity to change in this context, right? And so we are able to kind of discover some of the biases that existed in this data set, which are already reported to be along age and gender lines. And then the other thing is we go through with this interpolation that I described before. And so if we have a single point mapped to a bunch of other points, we'll slowly interpolate and spread that mass out from those other points and average the classification probabilities from the remaining people that you were mapped as similar to, from the bad credit to the good credit scenario. And just that with a kind of bird's eye understanding, we can see that the probability of being assigned a good credit label as a result of this interpolation increases from right to left, which also kind of shows us that our framework is just uncovering kind of meaningful recourse suggestions in the space that we're looking at. But that is my last slide. Thank you so much for sitting through that. Does anybody have any questions? I know that was a lot.
I have a question. I already asked one though, so if anybody else has a question, feel free to cut in line. I guess this is really fascinating. I have seen a few research papers that try to like approach this, but I've never seen one that does it in this sort of like ex post way, where you sort of like are almost like without trying to. Because I feel like a lot of times when I see people like the flagship example you brought up about like it's almost like posited as sort of like we have a problem with our data generating process where racism informs how many people are arrested, and so our outcomes are going to be picking up on sort of like a correlation in the fact that like our data are reflecting injustices, and so like looking for and like certain feature mappings are going to be like corrupted on that basis. And this is interesting because it sort of feels like it's like you kind of preserve. And correct me if I'm wrong, but it's like it feels like what this does is it doesn't necessarily change the feature mappings between like what is seen as predictive of default or recidivism, but rather sort of like kind of like adjusts the sort of the final classification so that those distributions are matching. So like the impact. So I guess to the extent that you have like a corrupted data generating process where like certain feature mappings that might be like in the criminal justice example, like you might have features that are predictive of bias, like blackness and various things that are maybe correlated. And those feature mappings in this structure, those feature mappings would be preserved, but they would just be sort of like distributionally adjusted in the final classifier so that it's sort of, you get kind of like an overall distribution that's kind of similar between like this like white high risk group and this black high risk group. So I guess like if you imagine like maybe there's like how there could be a spurious correlation between like like loving, I don't know, certain things that you would associate with, like if you take blackness out of the equation, then like maybe the machine learning algorithm says that listening to rap music or something is predictive of recidivism, and that's obviously it's just being biased.
Okay.
And so under this structure, I guess it would still preserve that feature mapping of like something that was associated with protected group, but then in the end, it would sort of adjust like kind of the final ranking so that the distributions match. Am I misunderstanding something?
No, not at all. I think that
Yeah.
kind of before the problem set up, part of the motivation is that we take the opinion that, you know, we're not going to solve discrimination algorithmically, right? I think the more important thing is to understand what the sources of it are and what our kind of ability to parse through data informs about that, right? And so if we kind of try and recreate some of these behaviors in the form of classification, now that kind of informs to us what the difference between these kind of two situations may be. And so leave the feature maps as they are, right? We're just kind of concerned about what happened to you, right? And if what happened to you is not the result of kind of changes in the feature space, right? And changes that we would like there to be in the feature space, then we can understand that some type of bias is going on, right? And so there's kind of not any notion of like corrective classification that's hiring, because that's like that's happening, because that's a slightly different problem. But rather, in the situation I do observe some process, how can I kind of use the tools I have to understand what the structure of bias is within that process?
Cool. Yeah, that seems very cool.
Thank you.
Hi, Kyuko.
Hi, how are you?
Great presentation. Thank you. It was really good. So at the end, you used the Wasserstein distance with p equals 2, right?
With p equals 1.
Sorry?
With p equals 1, we use the W1.
Oh, okay. So actually, that's my question. I'm wondering if actually there is any changes if you, I mean, the sensibility on this parameter. Have you studied it?
Yeah, if I can, let me go back to that slide if I can. What is going on? No, it's not what we want. Okay. So one of the things that's kind of weird about the Wasserstein distance is that there's like a lot of like really intricate math that kind of ensues. But I think one of the advantages of using the W1 distance is that it kind of becomes a norm over your measurable spaces, as opposed to kind of like a metric that has some kind of different properties. And so in just some of the proofs I've read and trying to understand more about what the metric is describing, we kind of get a lot more intuitive sensibility out of the W1 distance than we would out of the W2. And the other thing about the W2 is that we kind of have this exponential term at the end, which like, as you kind of increase from your W1, I kind of think about it as you increase from like an L1 norm to an L2 norm, for example, the type of distance that you're measuring is different, right? And so I think that certain types of differences as you change the W1 up to W2 maybe would be exaggerated, right? And so we can assume that differences between people are more meaningful in that context because we have a higher exponent on the cost function between them. We didn't do any specific experiments to answer your question about like the difference between W1 and W2. We kind of saw enough evidence in the literature to just kind of stick with W1, but I definitely think that is a question that I should have the answer for, you know, what if you use some other order for the Wasserstein distance?
Okay, got it. Thank you.
Yeah, no problem. Cyrus, you have a question?
Yes, I do. I'm wondering that if we're talking about the discrete case, it seems like the quantities we're measuring the Wasserstein distance between end up being analogous to the statistics used in traditional constraint-based fairness settings, like equality of opportunity and things like that. And I'm wondering if it's fair to view your setup as a generalization of those beyond discrete settings. And if so, if there are particular ways of parameterizing the distance metric and other aspects such that you recover traditional concepts of demographic parity?
Yeah, so let me make sure I understand your question. The first question is, to what extent does this generalize fairness metrics that we've seen already?
Yeah, I'd say so.
Okay, and so to that extent, I think it does so really well. There's some proofs that didn't make it to the presentation, but basically you can recover individual fairness properties up to a constant. You can recover like the Lipschitz continuity of another function. if you kind of have a low amount of Wallerstein distance based on the kind of comparison that you recover, right? And so in that extent, it does kind of generalize individual fairness. But the other thing regarding kind of these distributions that we're recovering is that these distributions are over the outcome space. And so we're kind of, instead of collecting binary labels, we're collecting, instead of collecting, are you above the threshold, are you below the threshold? I'm more interested in the granularity of, is there a 20% chance, 80% chance of 0 versus 1, right? And so in that sense, I think it adds an additional level of granularity, which makes it slightly different from the group fairness metrics that have been described already, because of that very, very minute difference in how you're thinking about the differences in outcomes. Does that answer your question?
Yeah,
Okay. Are you sure?
I think so.
Okay.
Okay, I'll ask the last question.
Yeah.
So when you are actually the slide that you just showed that you are setting this, yeah. So here, have you thought of like setting this cost function to something like more tangible? Like let's say, for example, in the case of credit cards, let's say the people who are not given loan, for example, they could be a higher cost for a single mom than for like somebody like a white single man that you are not giving the loan to. So have you thought of like assigning costs when you are doing this coupling with respect to like more tangible effects of not giving loan or giving loan or misclassifying basically?
Yeah, and so our recourse experiment kind of touched on that slightly. And so in the Wasserstein computation, to make this super explicit, the distance that you see here is computed over the outcome. So over the probabilistic vectors, which describe your outcomes, that's the thing that I'm trying to minimize. And so now if I have a policy, which is mapping everybody to an outcome, I just take the kind of the domain of that policy, apply my inverse, and now I can figure out who's kind of being mapped to what outcomes, because my policy function, let's assume it's 1-to-1, right? And so in that situation, we can define a distance metric over the individual features. And so in the recourse example, we kind of ignored immutable features and ignored kind of the non-actionable features and only considered, like in a Euclidean sense, the distance between your actionable features, right? And so in some sense, we did a little bit, but I also agree that you could apply like maybe a weighted distance function, right? Which would allow you to kind of make some things more important than others. And I think you would get kind of additional insight out of the framework if you did do something like that. And as long as it is still Euclidean in some sense, as long as the distance function is like lower semi-continuous, I think, then the Wasserstein distance is still defined, in which case you can still proceed. Cyrus, another question. Oh, you said the last question. Am I?
I'm not sure if Cyrus' hand is still on from before or he has a new question.
No, I just haven't mastered basic technology.
No problem. But yeah, that's all I have. Thank you so much. Sorry for taking everybody past time so much.
Yeah, let's thank Kyoyi Ku and all the other speakers, Meira, Samsun, and all of the attendants. Thanks for attending, and we will continue this discussion next Wednesday with a new theme. So I hope we see you all next week.